So let's begin what we'll be looking at in chapter 5.4. So in 5.4, we'll be looking at what we call sampling distributions, and then we're going to be talking also about the central limit theorem. So those are the two major areas that we're going to be looking at, and then we will work problems that relates to sampling distribution in terms of finding probabilities of sample means. Okay, so just to give you an idea what we'll be doing, before then, most of the things that we've been working on, it's over here. Like we have like a population, um, and in that population, we each member of the population is an X value. So over here, um, each each data point is X value. Okay, now I want you to think of this population as being here, all right, and then taking a sample out of this population. So you take a sample and then you calculate the sample mean, and then let's say, so you take the first sample, you get X bar 1. Then you take another sample, you get X bar 2. Then you take another sample, you get X bar 3, and so on and so forth. Now, assuming that you use the results you have here, the samples, the different samples you have, assuming that you use those to create like a histogram or some form of a distribution, all right? So now, all of a sudden, the numbers are no longer X values, but because you do the average of each number, now the numbers are now X bars. Like you see over here, that now every single value is an X bar instead of a regular. Now, because when you take the sample, you calculate the X bar, then you put the information down. Then you take another sample, calculate the X bar. So you're going to get a bunch of numbers whereby each number itself is an X bar. When you have that situation, we call sampling distribution of means. So sampling distribution of means is a situation where you have a collection. So sampling distribution of means. So sampling distribution of means is a situation where you have a collection of sample means. Right? So you have, let's say, X bar 1, X bar 2, X bar 3, X bar 4, so many of them, let's say X bar K. All right. So this time, the data you have, individual data itself is a sample mean. So in here, the individual data. So the individual data point is a sample mean. So if you have a group of data where the individual data point itself is a sample mean, then the collection of those sample means is called the sampling distribution of means. All right, so take note of what the name implies. Now, this is like a numerical data to let us have a much solid understanding. So let's take, for example, your population has how many? Your big N is 1, 2, 3, 4. Your big N has 4 members, 1, 3, 5, and then 7. And suppose you take repeated samples from of size n equals 2 from this population. So you go to the population, take a sample, calculate the sample mean, go to the population, take a sample, calculate the population mean, and so on and so forth. So we come to this population, we take a sample of size 2. It happened to have 1, 1, and then you calculate a sample mean and you get 1. So you're going to do all these ones. So these values that I have here, these values I have highlighted, each of those value is a sample mean. So over here, each one is X bar. The same thing. So these are all the possible samples you could get. So each one of these numbers is an X bar. So I can have a new collection of data. 1, 2, 3, 4. 1, 2, 3, 4, 2, 3, 4, 5. Then 3, 4, 5, 6. 3, 4, 5, 6. Then 4, 5, 6, 7. Then 4, 5, 6, 7. Now, this set of data that I have, how many is it? 1, 2, 3, 4, 5, 6, 7, 8. So I have 8 sample means. All right. So every single value I have here is a sample mean. Every single value, every one of them is a sample mean. All right. So if you have a group of numbers whereby every single data point is a sample mean, we call that the sampling distribution of means. All right. So when you see the word sampling distribution, it means you have a group of numbers whereby each number itself, or collection of values whereby each value is a sample mean. Okay. Now, so that's a concept I want you to understand. Okay. Now, if we have such a situation, all
Can
right.
you go back up for a second?
Okay.
Thank you.
So whilst I'm here, let me add some more notes. So here, let's say the population is the x values, x1, comma x2, comma x3, comma x4. For example, the population values were 1, 3, 5, 7. All right. Now the mean of this population, when you add these numbers, let me see, that is, what would that be? 16 over 4. So that is 16 over 4. The mean is 4. So mu is 4. All right. Now the standard deviation, I think, is 2.3. I calculated it somewhere. All right. Let me see quickly. Um, 2.236, 2.236, 2.236, 2.236. So the mean is 4 for these numbers. So for this set of numbers, the mean is 4 and the standard deviation is this. Now, for the sampling distribution, distribution. That's all these numbers, the x bar 1, x bar 2, x bar 3, up to whatever that is, right? Now, the question is, what is the mean of this group? And what is the standard deviation? What's the standard deviation of this group? Now, because every number here is a sample mean, the standard deviation here has another name. It is called standard error. So when you hear the word standard error is the standard deviation of the sampling distribution. All right. Now, the mean over here, the mean of the sampling distribution has a special notation. We write it as mu with a subscript x bar. And according to theory, the mean of this group is the same as the mean of the population. So for example, I don't need to list all these values. I don't need to list all these values, all right? If I know the mean of the population, then I know the mean of all these 16 numbers, okay? So the mean of these will automatically be 4. So that's one of the things I want you to know, that the mean of the sampling distribution is the same as the mean of the population. So that's one fact I want you to know. The mean of the sampling distribution is the same as the mean of the population. Mu x bar is equal to mu. The second thing I want you to know is that the standard error, which is the same as the standard deviation of the sampling distribution, is the standard deviation of the population divided by square root of n. Now note that over here n is equal to 2 because we selected a sample size of 2, right? Each sample has 2 members. Each sample has 2 members. So the n is 2. So we could write this as 2.3 2.236 divided by square root of 4. I don't know what that will give you, but I want you to know that the standard error is sigma over square root of n. So number one, the mean of the sampling distribution is equal to the mean of the original population. The standard deviation of the sampling distribution, which is also called the standard error, is equal to the standard deviation of the population divided by the square root of the sample size. Divided by the square root of the sample size. So these two information are crucial for everything that we're going to do beyond this. All right, and that is what this slide is about. All right, so the mean of the mean sampling distribution is mu. The standard deviation of the sampling distribution is sigma over that. Now the standard deviation is also called the standard error, right? The standard error. So if the original population, if this is the original population and this is the sampling distribution, then if the standard deviation is sigma, the standard deviation of this group will be sigma over square root of n, where n is the sample size. So have these two things at the back of your mind. Okay, so I've shown you two things, 1 and 2. Now let's look at so this is a question that we were looking at. So we've done this already. I just showed you n is 2. So for each problem, know the population side, know the sampling side. The mean of the population is 4. If you find the average of this, that gives you 4. If you find the standard deviation of the same thing, that gives you this. The mean is 4. The standard error will be this population mean divided by square root of 2, and then that gives you this value. Okay, now let's see the next problem. So some of your homework problems will look just like this. All right, so when you take the question, create create like a T something. Oh, what happened? Have the population side and have the sampling distribution side. Population side is x1, x2, x3, going, and sampling distribution side is x bar 1, x bar 2, x bar 3, and so on. Every number here, it's an x bar, every number in the population side is a regular X, right? So in this question, usually a question will give you only the population side. So the mean they're giving you here, mu is 63, is only for the population side. Yes, Alex.
Why do you put x bar k at the end of sampling distribution?
Oh, because um, the number of all the possible samples, usually we use the notation K.
Okay, thank you.
Okay. For example, let me see here. You see over here, we end up here like K is 16, because if you take a sample of size 2, all the possible samples will end up to be about 16 of them. So even though N, oh, what happened to my calculator? Okay. So even though N happened to be 2, all the possible samples, so it's like 16. You have like 16 of these sizes. Okay, so that's why I put the X back here, but that's a very good question. Okay, so what the rule we just learned says that if the mean is 63, then the mean of all the X bars, mu X bar, will also be 63. That's one of the rules we just learned. Then they said that the standard deviation is 11. So sigma is equal to 11. So we could say that the standard error, which is sigma x bar, will be what? 11 divided by, they always have to tell you the sample size. Now they said a sample of 100. Random samples of 100, so n is 100, right? So n is 100. So let me write, it's always good to write a formula before you write anything. So this is sigma over square root of n, so that will be 11 divided by square root of 100. So that will be what? 11 over 10, and that gives you 1.1. So sigma x bar is 1.1. And note, this is the same as what we call the standard error. So the question says, find the mean, find the standard error of the sampling distribution of this side. All right, so the answer will be this and this one and that one. All right, let's look at more questions. So this is another question. So I'm going to break every question into two parts, the population part and then the sampling distribution part. Population part is always x1, x2 up to x big N. Sampling distribution part is x bar 1, x bar 2 up to x bar k, where k is a number of possible samples. Question said that the mean mu is 135, which means that mu subscript x bar will also be 135. That is automatic. Then question said that standard deviation is 18. So sigma is 18. So sigma x bar is sigma over square root of n. I always forget to write my n. Let me write the n here. So n is what? Sample size is 4. N is 4. So I'm going to write 18 divided by square root 4, which gives you 18 over 2. That gives us 9. So we would say that the standard error is 9. This is, so the mean is that, the standard error is that. So those are some of the questions that you're going to be working over tonight. Now, let me now talk about what we call the central limit theory. All right, the central limit, the T didn't come well. The central limit theorem. Now, what a central limit theorem is saying is that if samples of size n greater than 30 are drawn from any population. So let me put it this way. Suppose this is a population site and this is a sampling site, sampling distribution. Now, usually this as n equals to a number, right? So this is mu, and then you need sigma, and then the shape. So the central limit theory talks about the shape of the distribution. Now, it is saying that if the shape is distribution, any distribution drawn from any population, so any distribution, if the shape is any distribution, as long as, so let me write shape here. So this is mu x bar and this is sigma x bar. All right. This now it's saying that if your n is greater, if your n is greater or equal to 30. So let me just write greater than 30 because I read on that. Greater or equal to 30, then irrespective of the shape of your distribution, the shape of the sampling distribution is going to be approximately normal. It's going to look normal. Your x bars, the shape of your x bars when you put it into a distribution, as long as each x bar is what? Greater than 30. As long as each x bar, sorry, as long as your n, yes, as long as your n, each sample size is greater than 30, right, the shape of your distribution will be normal. So that's what the central limit theorem. There are two aspects of it. This is number one. Now, the second aspect of the central limit theorem says that if the shape is normal, then if the shape of the original population, if you started with a normal distribution, then the shape of the sampling distribution, the shape of the sampling distribution would automatically be normal. Start with normal, shape sampling distribution will be normal. If you start with normal, this will be normal. Now, this says that if you start with a distribution that is not normal, then this will be normal provided, so this is normal provided n is greater than or equal to 30. That's what this is saying. All right, so take note of the two aspects of the central limit theorem. If you start with normal, the sampling distribution, the shape of the sampling distribution would automatically be normal. If you start with something that is not normal, then the only way you get a normal sampling distribution is when the sample size is greater than 30. All right, and that is why it's always good when we write these things. We're now going to be writing the shape. We're going to write three information here: the mu, the sigma, and then the shape. Okay, so that is the second one I'm saying, that if the original population is normal, then the sampling distribution will be normal irrespective of your sample size. It doesn't matter. Once you start with normal, you're going to end with normal. Okay, now let's see ways that it makes sense. So this is just a repetition of it, right? Start with something that is not normal. As long as your n is greater than 30, you are going to get normal. Start with normal and you automatically get normal. That's what this is saying. So this side, the sample size is important. This side, the sample size is not important. All right, so let's look at the question. Now, so For all these questions, usually they're going to talk about sample size. Like here, for example, they said 25 randomly selected students. All right, so they're giving you a sample size. So let me create a small that thing that I've been creating. So for every question, you may need to create this to help you. The population side and then the sampling distribution, sampling, sampling distribution side. It's always good to have your know your n. So mu, sigma, and then the shape. Okay, so what is the question saying? The question is saying that the average is 78. So let me write it out. Average 78. Now, question is saying that the standard deviation is 8. So sigma is 8. Now, then they said a random sample of 25. So n is 25. Well, there's something very important they mention here. Say if the test scores are what? Normally distributed. So the shape is normal. So let me write mu x bar, sigma x bar, then shape over here. So it says that if the shape here is normal, the shape over here will automatically be normal. No two ways about it. All right. That's one of the areas of the central limit theorem. So according to what we've learned, if the population is 78, population mean is 78, then the mean of the sampling distribution will also be 78. Over here, this is sigma over square root of n standard error. So that would be 8 over square root of 25. That would be what? 8 over 5, 1.6. So how would I do? Now, question says find the probability, right? Find probability. Now, it's not just going to say find probability, but it says find probability of the mean, meaning that it's dealing with sampling distribution. Why? How do we know? Because we know sampling distribution, every value here is a mean, right? Every single value we have over here is a mean, xk. So that is why they say find probability of the mean. Now sometimes it will say find probability of the average. All right. The moment you see word probability of a mean, probability of an average, they are dealing with sampling distribution. Because in this case, according to the central limit theorem, this sampling distribution is going to be normal because we started with a normal. We now can draw the normal curve. So I can draw the normal curve over here in order to answer the question. First, the mean is 78. Now, question said from 75 to 79. So I'm going to make a line and I write 75 here. Then I make another line, I write 79 over here. Then I shade in between because they said between those numbers. So I want to find the probability in this area, right? If you want to find probability, then you're going to use normal CDF, right? That is how we find probabilities. We use normal CDF. So how would I do this question? I'll do normal CDF from, let me write this, from 75 to 79. The mean is what? 78. The standard deviation is this one. It's 1.6. Take note of that. Why? Because the standard deviation on this side is the standard error. This is the standard error. Because we calculated the standard deviation on this side to be 1.6. And then you work it out. If you work it, that will give you this 0.7 Um, yes.
Do you always use the standard deviation from the sampling distribution?
You use the standard error.
So is it always the one from the right side and not the left?
Always the one on the right side. Provided the question says find probability of a mean, right? If it says find probability of the mean, then you use the standard error. Okay, someone said you got a different answer. Tell me what you got. Normal CDF 75, 79, 78, 1 point. Okay, so I had the wrong number here. All right, so I'm gonna change it based on your recommendation. 0.70361. Okay, based on your recommendation. Hopefully your recommendation is correct. After class, I will check it. All right, let's take another question. Okay, so in this question, once again, look at how the question is worded. Find probability of the mean. So it means you're dealing with sampling distribution. Anytime you're dealing with sampling distribution, draw this thing that I've been doing here. All right, have your population side, have your sampling distribution side. All right, always know what the n will be. All right, so when you read the question, the n happened to be 50. Over here, the mean, they said the mean is 34,000. The standard deviation is 2,500. The shape, did they say anything about the shape? They didn't say anything. So we're going to say any shape. Any shape. All right. Now, mu x bar will be 34,000 because they are going to be the same. This is always going to be the same as that. All right. Then sigma x bar is going to be 2,500 divided by square root of n. Actually, let me write a formula first. All right. So let me write a formula first. It's always good to write a formula. Sigma over square root of n. So that will be 2,500 over square root of 50. And you could just leave it like this for now because we're going to use it too. Now, the shape, according to the central limit theory, it says that if you have any shape, then the condition to be normal is that your n should be more than, greater than or equal to 30, right? So this n, it's more than 30. So that is good for central limit theorem. So the shape is going to be normal. So even though nothing is said in this example about the shape, we know it's going to be normal because of the central limit theorem, because our n is greater than 30. All right. What should I do then? I now can draw a normal curve. So let's draw a normal curve. The mean is 34,000. Now, 34,000, I have too many zeros here. Question says greater than, we should find probability of a mean. So we are working from this side, greater than 35,000. So 35,000 is over here. Greater than that, so I'm going to shade to the right, meaning that I'm going to infinity. Therefore, I will do what? Normal CDF from 35,000 to 1 million. The mean is 34,000. The standard deviation is 2500 over square root of 50. You can put the whole thing in the calculator. The calculator understands what you are doing. All right, so you can put the whole fraction in here. You can put the fraction here. The calculator can do the problem for you without a sweat at all. Okay, so my answer I got here is 0.0 0023. Somebody could check for us. I need auditors for the class. Ooh, hooray! Wonderful. That is great. That's great. So I got it right. Okay, let's look some more examples. So you see the pattern of the questions. Always he's going to say find probability of the mean or find probability of the average or something like that. Look at this question. Probability of the mean. Probability of the mean. All right. So when you see questions like that, when it talks about probability of the mean, know automatically that is a sampling distribution question. So you have original population and then you have the sampling distribution side. Always you need your n for sampling distribution. So what is the mu for this group? They said the mean is 313173. Then they said the standard deviation is, so sigma is what? Where is it? 1120. They said the shape is normal. Now, if shape is normal, it means the shape over here would also be normal for sure. If it's normal here, this would be normal. It doesn't matter the sample size at all. Okay, now let's fill out the other one. Mu x bar will be 3173 because we always say that this and this must always equal. Then sigma x bar, which is called the standard error, it's sigma over square root of n. Where's our n? N is 25, sorry. Usually I like to write an n ahead. So that will be 1120 over square root 25, which is 1120 over 20 over 5, right? Square root 25 is 5. Is it still 5? Okay, so let me hope it is still 5, right? 5, and that is 224. You actually can put the whole of this in there. It doesn't really matter. All right, so let's go to the question. Because it's normal, the shape will be normal. I can confidently draw a beautiful bell curve, right? And then put a mean in the middle, 3173. Then now they said find the probability that it is less than 2700, less than 2700. So I would put the 2700 over here, 2700, and I'm going to shade this side. So this is from negative infinity to this number. So I would say normal CDF from negative 1 million to 2700. The mean is 317173. I'm sorry. The standard deviation is 224. So note this is the standard error. All right, you always plug in the standard error. You always plug in the standard error, and then you work it out. Now I'm going to write my answer. Somebody confirm that for me. All right, so this should give us 0.0174. Oh, I got it right again. Yay. Wonderful. Beautiful. Now, so this classwork is our turn. All right, so we're going to do this before we leave. If we don't finish, you are not leaving. Okay, so you're going to do the problem population side. I'm going to call names, sampling distribution side, the N. All right, so I need a mu, I need sigma, I need shape. I need mu x bar, I need sigma x bar, and I need shape over here. Okay, so let me start with Claire. What is the sample size?
100.
Very good. Good start. All right, Jack, what is the mu from the population side? What is mu?
63.
And what is the standard deviation, Jack?
11.
Okay, thank you. Now, Anna, what is mu x bar? Yes, Hannah? Mu x bar. Okay, Mike, what is mu x bar? Is Mike in class? Michael? Okay, Brianna helps you. 63. Okay. Let me see. Sophia. Oh, what is sigma x bar? First, what is the formula?
Um,
Sigma over.
yeah, over square root of n.
Good. So what should I write?
11 over the square root of 100.
Good. So that's 11 over 10, and that's 1.1. Okay, very good. That's good. Now, it looks like this is any shape, right? They didn't say anything about the shape, so we say any shape. But the sample size is 100, right? So first question says, what is the sample size? We know the sample size is 100. Second question says, what is the mean? This is 63. Third question says, what is the standard deviation or sample distribution? So they want standard error. This is 1.1. Then so we are now over here. But first I'm asking what is a shape? So Melissa, what will be the shape of the sampling distribution? Yes, Melissa. We gotta hurry up. Normal. Okay, good. All right, so the shape will be normal. Means that for each of these three questions, we have to draw the normal curve. All right, so let me start with the normal curve. The middle is 63. So when we look at question D, it says something greater than 74. So we're going to draw a line for 74, and then greater than, we're going to shade this way. All right, so Justin, when I write for D, when I write normal CDF, what should I write inside? Justin. Yes, Justin. Okay, Ryan. Is Ryan there? What's happening? People just put the thing on and they're not in class, they just put it on for me to know they are there. Okay. Sydney D. Your mic is not working, Ryan. Okay, so Sydney D. When I write normal CDF, what should I write inside? All right, Kelsey, help me. Okay, so 74, good. That's good. Olivia wrote it for us. 74 to 1 million because it's infinity. 1 million. Then we have 63. Then we have 1.1. Very. Olivia, you mess up, right? We should write 1.1 because that's the whole reason why we're doing this. That we're never going to use this if you're dealing with this group. All right, we're going to put 1.1 because that's the standard deviation in this group. Okay, you say why wouldn't it be? Because the standard error. All right, Sydney, I see your remarks. The standard error here, standard deviation here is 1.1. So that's what you put over here. Yes. Okay, so let's look at E. So E, let me draw the diagram over here. So for E, they said less than, okay, 63, and they said less than 63. So somewhere like this, negative infinity. Oh, you can put 11 over 10. Yeah, that's still fine. Yeah. Okay, so could someone tell me what E I should write after the normal CDF? Yes.
You
What's
know
your
that.
question, Alex?
Oh no, I was going to do the answer.
Yeah, I'm ready.
Okay, it's negative 1 million.
Okay.
Then you have 63.
Good.
Then you have 63 again, and then
Good.
1.
Excellent. 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 Okay. So I have 1 minute for the last one. F. Normal CDF. Can I get a volunteer for F? Okay, Sydney, let's go.
So
I'm
it'd be
ready.
normal CDF and then
Uh-huh.
52, comma,
Good.
74,
Good.
comma, 63, and then
Good.
1.1.
Very good. And then that's it. That's